In a well-publicized report released early this year by the World Bank, graphite was identified as a mineral with the highest projected increased demand by 2050 relative to today. For that reason, it gives me a great pleasure to introduce our second speaker, Nelao Naimbale, to talk on the Okanjande graphite deposit. Nelao is a geologist from Namibia. She earned her bachelor in geology from the University of Namibia and went to complete her master's at China University of Geosciences, working on the topic she is going to present on today. At the moment, she is working as a part-time lecturer in exploration, geochemistry, and geostatistics at University of Namibia. But she is eager to hear about PhD or exploration opportunities in economic geology, especially in either graphite or African copper belt space. For now, I'll turn over to you, Nelao.
Thank you, Filipa. And thank you for everyone for joining this talk. So without wasting time, let me just start over. Let me start with my presentation. So as you can see from the title, I'm just going to talk about the origin of graphite at Okanjande graphite deposit, which is in the Damara belt, Namibia. So basically, like graphite is in demand right now, or let me say, according to the World Bank, the demand of graphite is going to increase by 2050, and graphite is widely used in, in lithium-ion batteries, as you can see, as the technologies are, are shifting to green technologies, and most of the people are going to use electrical cars, and it's also now graphite is used in fuel cells, in refractories, in brake linings, pencils, and in lubricants. So the demand for graphite is increasing. As you can see, that is the demand of graphite in 2018, and you can see that is the projected demand of graphite by 2050. So you can see the world is shifting towards green technology, friendly environment. And now here you can see again, this is a projection from the World Bank, where you can see the share of mineral demand from energy storage. As I talked earlier, that graphite is the demand of lithium-ion batteries are increasing. So the lithium-ion batteries that are used in electric cars, they actually consume more of graphite than lithium. Okay, so now coming to Okanjande graphite deposit, it's located in, let me say, north central Namibia, 14 kilometers from Oshibarongo, and round about less than 200 kilometers from the capital city of Namibia, which is Windhoek. And the Okanjande graphite deposit is within the Damara belt, which is part of the Damara orogeny. And so you can see the geology of Namibia is divided, the Damara orogeny is divided into 3 belts. You have the northwestern Chalco belt, you have the Damara belt, and then you have the Harib belt in the south. And most of the exploration work in the past years has been focused on the Damara belt, but now in the recent years we have seen increase of exploration work in the Chalco belt, with the southern area still being underexplored. Okay, now the Damara, the Damara belt, where the Okanjande graphite deposit is hosted, is further divided now into different zones, from the south to the north, to the south. And you can see that here there is our deposit, Okanjande graphite deposit, which is located in the north central zone. And now this is just the Damara sequence rocks, or the groups of the Damara belt, which we have the Nosib, which is the oldest, we have the Otavi, Malden, Swakop group, and then the Nama group, which is the youngest. As you can see now, this is the central zone, the Damara sequence rocks in the central zone, where Okanjande graphite deposit is located. And most of the rocks of the Okanjande graphite deposit falls within the Nosib groups, the quartzite, and then there's the marbles of the Sokop group. Okay, now when it comes to graphite occurrence in Namibia, we have 3 major occurrences, which is we have the flake type, which is Okanjande now, and then another one, Belgrano 72. And then we have a vein graphite deposit, which is located south of Namibia. This one has been mined before, and I think it's still, it might go in production soon. And yeah, those are the 2 types of graphite deposit. And basically, when it comes to graphite, there are 2 types of models. You have the syngenetic model, where you have now your flake type graphite. And then you have the epigenetic model, where you the vein graphite deposit falls. So just a bit of history. It was discovered by Rosin Uranium, and now it's owned by Imerys Graphite and Co. and Geco Graphite Namibia. And then these are the, you know, the indicated, the measured resource and indicated resource for graphite. There's quite a high amount of rutile. That's why they put the indicated and measured resource for titanium oxide. Okay, now coming to the local, coming to the local geology of the deposit. You can see now the graphite is hosted within the graphite quartzites. As you can see that in green, that is your graphite, your quartzite. And then the dark ones, or the gray, that is your quartzites now, which we call graphite quartzite because of the high amount of graphite. And then these quartzites, they form prominent hills around the deposit areas. And then in the valleys, that's where you have your Sokop marbles and calc silicates. And then there are numerous granitic and pegmatite intrusion within the deposit. So as I mentioned, the graphite is hosted within the quartzite, which we term feldspathic quartzite because they have a high amount of feldspar in the quartzite. And then you can see here that there is quite, this area has been quite, it's folded, and then there are also major faults around the deposit area. As you can see, also some of the foldings in the quartz veins within the, you know, the graphite quartzites. And you can also you can see this dome structure also within the graphite quartzite. So and then here, this is your graphite quartzite, and then you have the pegmatitic intrusion right within it. So now moving on to petrography, the graphite quartzites now, as we term it, because of the high amount of graphite, you can see now that is your graphite within the quartzite, and then you have your quartzite. And then now one major mineral which is occurring in this quartzite, we have silimanite, which I'll talk about later on as we move on, because it's forming quite a texture within the ore. Okay, now this is a petrography of quartzite itself. You can see that the graphite quartzite is silimanite, but if you look at the quartzite, which is not with no graphite or so, there is no silimanite. That is one major difference between the graphite quartzite and the quartzite. There is here you can find muscovite, K-feldspar, plagioclase, and so on, but then there is no silimanite. Right? Okay. Now, now the marbles, which I term the Sokop marbles. We have some with less amount of graphite, and then you have some which have a high amount of graphite. As you can see, this one is a bit darker, and the other one is a bit light. And then the major mineral which occurs within the marble is calcite, and you have some actinolite and plagioclase, and also some biotite. And then there is also calc-silicate, which has also a lesser amount of graphite. You can find also some plagioclase, and then some actinolite, and also some biotite. Okay, now this is just a sample of now granite within the that includes the quartzite. This granite is more like altered because you can even see like from the sample itself. And then there are some granites which are with a high amount of plagioclase, and then there are some K-feldspar. And then there is also a presence of rutile in the granite. Okay, now the Okanjande ore body is previous, like when it comes to Rossing, when they did exploration, they say the shape is a kidney shape, and then when the Gecko company termed it as a complicated irregular dome structured body. As you can see, the faults that transcend the ore body, that makes it more complicated. And then it's 600 meters long on the axis, the long axis, and then 300 meters wide. Now now the ore body is divided into weathered and fresh ore. As you can see from this, these are just simple ore body logs, just to indicate that we have weathered ore and fresh ore, that this normally until 20 meters from the surface, until 20 meters, that is weathered ore. And the difference between our weathered ore and fresh ore is that in fresh ore you find sulfide minerals, while in the weathered ore you find more of jarosite, which a mineral which resulted from weathering of sulfide minerals. Okay, now the ore texture, we have three types of ore texture. We have the banded one, we term it gneissic, and then we have the porphyroblastic, and then the migmatitic ore. And then these porphyroblasts are actually sillimanite, which only occur within the graphitic ore, and the graphitic quartzite, and not within the barren quartzite. And now the ore petrography of quartzite, we can see now that's your graphite, we have rutile. And then now when it comes to rutile, there's no really relationship between rutile and graphite. They are quite independent of each other. Although when it comes to sulfide minerals, you find inclusions of sulfide minerals within graphite. As you can see here, they are intertwined into each other. And also you find some of the graphite within the sulfide minerals. As you can see, that is your graphite within the sulfide minerals. And then now the sulfide mineral present, we have sphalerite, pyrrhotite, chalcopyrite, and then pyrite. And also then we have some quite high amount of rutile. Okay, now moving on to geochemistry, I just tried to do some major elements. But doing major elements and trace elements for this quartzite, it was quite, let me say, it was quite difficult because of the high amount of quartzites. When the samples were taken to the lab, they had to take other measures in order to stop the graphite interfering in the outcome of the results. As you can see now, here we have high amount of silicon in the graphite quartzite, in the quartzite, and then we have actually higher amount of titanium oxide in the, we have high amount of titanium oxide in the graphite quartzite, which is now rutile. Okay, now this is the rare earth elements. The diagram now here, you can see that there's enrichment in light rare earth elements, and then with a negative EU anomaly, and then we have a depletion or a flat pattern when it comes to high rare earth elements or heavy rare earth elements. And then now when it comes to trace elements, we have enrichment in rubidium, thorium, uranium, and lead. And then we have a depletion in barium, niobium, strontium, and titanium. And then when it comes to granites now and pegmatites, there is also an enrichment in light rare earth elements, a depletion in heavy rare earth elements, and then a negative European anomaly. And then now, since there is high amount of sulfur, I tried at least to just compare now the amount of carbon and sulfur in the deposit to see if there's any relationship. But as you can see, like from the diagram, there is not really, you can't really say there's a direct or indirect relationship between the two. As you can see, this sample, it has quite high amount of sulfur, but then the carbon amount is more moderate. Okay, now moving on now to the carbon isotope, which is more important now. It's an important part of this study. Is Now, the carbon isotope from graphite of the graphite quasite, which is I abbreviated here GQ, we have a carbon isotope in the range of -13.36 to 19.58. And then we have in the carbonate rocks, we have we have a range which is -4.54 to 7, which is around the mantle, range, and then other range within the carbonate rocks. And this is the carbon isotopes from the intrusive rocks. And then I also analyze the carbon isotope from calcite. This is basically, this is for the purpose of determining the isotopic exchange between carbon in quasites and, graphite in the carbonate rocks, so that I can determine the temperature of the deposits. I also did now the sulfur isotope of the sulfides. As you can see, all the minerals, they have a sulfur isotope within the range of -5 to 5, which is near zero. Let me say it's more of a magmatic origin. Okay, now when it comes to graphite, we have 3 types of graphites. We have now the flake type, the amorphous, and the vein. And then these two are of amorphous and flake, they are of syngenetic origin, while the lamp chip or vein is of epigenetic. And now the features of Okanjande graphite is they are disseminated, they are needle-like and platy, flakes, and they are well crystallized, as I'll show in the next slides. Okay, now when it comes to graphite, for you to determine the crystallinity of graphite, you have to consider the graphite morphology. And then now, because when graphite is formed, it goes, the organic or carbonaceous material, they go through diagenesis and metamorphism, which is called graphitization. And now as temperature increases or as metamorphism increases, the crystallinity of the carbon materials, organic matter also increases, which means graphite is being matured as temperature increases. So now with the calculation using this Shira's equation, and the results from XRD, I came up now with the diagram in this this figure, where I use the interplanar spacing and the crystallite size to determine now the maturity of graphite at Okanjande graphite deposit. So you can see now these samples compared now to other samples from India and from Finland, you can see that the samples of Okanjande graphite deposits are plotting within the graphite zone, the graphite, with only one sample that is plotting in disordered graphite, which means you can say that the graphite at Okanjande deposit is quite matured, or it's of high crystallinity. Okay, now coming now to the temperature, I use now the degree of graphitization to calculate now the metamorphic temperature using the equation which was derived by Weather. And then I also use now the carbon isotope fractionation or isotopic exchange between calcite and graphite within the carbonate rocks. So, so from this table, you can just see now this is the temperatures that I calculated using degree of graphitization from the XRD results. You can see this is the lowest temperature, 386 degrees Celsius, and then the highest temperature is 706. And now coming to this figure was just to compare that as degree of graphitization is increasing, the temperature is also increasing. That's why you see that there's a direct proportion between the two, which means the graphite at Okanjande is well crystallized as metamorphism progressed. And now coming to the temperature from the carbon isotopes, I used actually for this one, I used different equations which were derived from by several scientists or by several authors. And then I found that this equation by Naimbale 1992 was more acceptable as other equation yielded high temperatures or very low temperatures. As you can see that this equation, the first equation, which was derived by Bottinger, is giving a 956 degrees Celsius, which is quite high for Okanjande graphite deposit, provided that if you look at the mineral assemblages, with sillimanite being the mineral in the upper now amphibolite, this temperature will be quite high for Okanjande graphite deposit, and just for the central zone itself. So this now, from this calculation, we have a temperature of 684, which is the highest, and then the temperature of 205, which is the lowest. And all this was done from the graphite and the calcite, from the marble and the calc silicate. And I also took this sample from the graphite quartzite, where there are calcite veins, because there is quite some presence of calcite veins within the graphite quartzite. Okay, now this figure is just showing the carbon isotope fractionation between the graphite and the calcite within the carbonate rocks. As you can see now, this is unmetamorphosed, or it's a green schist fascist, and the amphibolite, and this one is a granulite fascist. So as metamorphism increases, the isotopic exchange between calcite and graphite takes place, and then the isotopic fractionation also decreases. That's why you can see that in granulite fascist, the isotopic exchange is quite low, while in the unmetamorphosed or green fascist, the carbon isotopic fractionation is quite high. And then this study, which is Okanjande graphite deposit, you can see it in dark right here. So it falls within the amphibolite facet, with just one sample which fall within the range going into the unmetamorphosed zone. Okay, now the source of carbon that formed graphite at Okanjande graphite deposit. Okay, now we have three main sources. We have the organic, or the carbonaceous materials, which are with a range of -10% to -40, with an average of 25. We have the mantle derived, which has a carbon isotope around 7 degrees, 7%. And then we have the carbon isotope from carbonates, with a range near 0. So now from this deposit now, within the host rocks, we have this range of -15 to -21, which is within the range of organic. Within the intrusive rocks, we have -17 to -18, which is still within the organic range. And then within the carbonate rocks, we have a range, we have quite some results. We have -4 to 7, which is around the mantle derived graphite or carbon. And then we have -11 to -15, and then a 22.68. So we can say this is rather, from some of it, it's either organic, and some of them came from devolatilization of carbonate minerals, rather than from being derived from the mantle. Okay, now since we have a quite high number of sulfide minerals at Okanjande, I also did now a sulfur isotope, and then it shows that all the samples that I did, where I got sulfur from the pyrite, pyrrhotite, and from the chalcopyrite, they are all in the range of negative. They are all in the range of -5, in the range of -5 to 5, which now is of magmatic origin. So I try to compare this with the results which it came from Namibia gold deposit. It's also within the central zone, and then and also other deposits within the central zones, which give results which are also close to magmatic, but others also give a quite a high range of results. Okay, now coming almost to the end of the talk, we have now to sum up now on the formation of Okanjande graphite deposits. Okay, the central zone is a high temperature, medium to low pressure zone. And now the Damara orogen was formed as a collision between the Congo and the Kalahari Craton. That was some years around, the Damara episode initiated between 1,000 and 900 million years ago. So now the nocive sediments, as this episode started, sediments were deposited within the area where Okanjande graphite deposit is, and then this sedimentation took place within, around the age of 800 to 750 million years ago. Now, also around this time, rifting started or commenced. And then it ended around 500 million years ago. And then now metamorphism began. So the fact that Okanjande graphite deposit is of flake type, and when it comes to flake type, it's referred to as metamorphic origin, which means the sediments that were deposited within the Nosib group or within the area of Okanjande graphite were also deposited together with some microorganisms which are rich in carbon. Then as metamorphism progressed within the central zone around 540 to 510 million years ago, these carbonaceous materials were then metamorphosed, and then they formed the flake type graphite at Okanjande graphite deposits. Okay, so now this is how now this sediment came. They were deposited within the Nosib group and the Swakop group, and then this now high temperature conditions within the central zone now, or in the regional metamorphism that took over or took place within the central zone, transformed this now carbonaceous material through the process now of qualification and graphitization. So now, just to sum up, we can say now the origin of graph or carbon responsible for the formation of graphite. Now at these deposits, it's mainly organic, as we have seen from the carbon isotope that it ranged between -10 to -40, and also from the devolatilization of carbonate minerals. And now also from the graphite morphology study, it shows that the graphite is of high crystallinity at Okanjande. It's graphite which is ready, to be used for lithium-ion batteries. It's graphite. When you're talking now about graphite mine, these are the type of graphites that you can use. Good quality high crystallinity means good quality, and also the size at Okanjande is you have some fine flakes, we have some medium flakes, which is also quite good for for the industry. And now the peak metamorphism now at Okanjande now, as we saw from the results that temperature that I calculated, it is around 700 degrees Celsius, which correspond to some of the temperatures that were calculated within the central zone, and it's also correspond to the temperature of the upper amphibolite fascists. So now petrographic studies were also trying to see if sulfide minerals have an influence on the graphite grade, but they don't have any influence. Rather, these two minerals, they are all independent of each other. So now overall, I would say the results now from Okanjande graphite deposits, or the study that I did, I would say the flake typist Okanjande graphite deposit is of metamorphic origin, and now the source of carbon that formed the deposit is of organic origin rather than mantle derived or devolatilization from carbonate minerals. So basically, this is all I have for this talk. And then I just want to give now special thanks because I did this research at China University of Geosciences during my master studies under the supervision of Professor Jiang Xiaoyong. And then this research will not be, I will not be presenting Okanjande graphite deposit if it was not for Imer's Graphite and Carbon and Gecko Namibia. They are the one who opened their doors so that I can, I'll be able to take whatever data I need, whatever sample I need, so that I'll be able to get all these carbonate result, carbon isotope results and so on. And then also now, but most importantly now, this research will not be possible if it was not for Professor Fred Kamona of the University of Namibia, but he's retired now. He retired towards the end of 2019. He's the one who initiated this project. Of course, I came up with the topic, but he's the one who initiated. So many thanks to all these people who made sure that this research was possible. And thank you for everyone for coming and for tuning in today's talk. Filipa?
Okay, thank you very much, Nelao. It was a really nice overview about these graphite deposits. So, Kathryn, do you want to join us?
Thanks, Filipa. And thank you very much, Nelao. That was really interesting. And as you said, graphite is going to be really important. It's essential for batteries for electric vehicles. The World Bank is forecasting significant increases in demand. And yet we don't hear that much about graphite compared with some of the other more, what people might term exciting raw materials. So it's really good to see so much detailed work being done.
Oh, yeah.
I've got some questions first about the sort of regional context. So you've shown that these are it's polybiogenic carbon, it's syngenetic, but what's the sedimentary setting in the Damara origin? You said rifting, but are we looking at, for example, shallow marine? What's the sort of setting where these sedimentary rocks would, or metasedimentary rocks now, were deposited?
I would say maybe shallow marine, but let me say I was more focused on, just the deposit itself and, the carbon carbon isotope rather than the settings. And actually because if you look at also this deposit, when it comes to structural geology, it's quite complex. Okay. So that is something that I really, considered, but the fact that when I took on this project, it's like it was basically from scratch. I thought that if I'm going to I might end up putting more, more incorporating more topics in this, which it was going to take up much of my time. So I think that is a topic that will also be good for research, because there is quite a large number, or let me say, this deposit still has potential for so many research, even PhD, masters, and so on, even undergraduates can do research, because there is also a matter of geochronology, which can also be done on these deposits, because there are no any age dating. Although I have done some, which I'm reviewing them, probably maybe for publication also.
Grand. And so I think that means that my second question might also be an answer of this is more work we need to do. But I thought that it was really interesting when you link together your temperatures, which go up to quite high, and then also the fact that there's some evidence of mantle-derived material in the sulfides. I'm just wondering, is the regional metamorphism really the most important control on the graphitization, or is it possible that contact metamorphism associated with the intrusion of the granitoids is also important?
No, I think I thought of that, and I also, I think contact metamorphism also has to do with this, because there's quite a high, large amount of marbles within the areas, or let me say the carbonate rocks, and also now intrusions. And so I think contact metamorphism might also be contributing to these temperatures, rather than just focusing on regional metamorphism.
I think that could be really important in terms of understanding the mineral system, because if you think, okay, you need contact metamorphism, you want to look for areas where the right types of sedimentary rocks are also associated with intrusion of granites. So it's a very important part of the story. So one last question before I hand over, because I see there's lots of questions in the chat. You mentioned quite a lot of rutile, although your titanium contents weren't that high on the trace element plots. But I just wondered, has anybody looked at the possibility of extraction of rutile as well, to get at the titanium, or is it non-economic, even though there's quite a lot of it there?
No, I think let me not say I will not be able really to answer on this, but I think the company itself, Imeris and Geco, they have looked at this because they have also their resource and reserve. They have also indicated the grade, or I mean the tonnage and grade for rutile, for titanium oxide. So I think they have been looking at that.
Yeah, okay, that's very interesting.
Yeah, and actually the age that I'm talking about on the deposit that I did, that I'm reviewing, I actually did them on rutile. I dated the rutile.
That would be really useful as well, because that would give you the metamorphic potentially.
Yeah.
Brilliant. Thank you, Nelao. It's really interesting. I'm going to hand you back over to Filipa because I know there's more questions for you in the chat.
Yes. Thank you. Thank you, Kat. So we have a couple of questions. The first one, Leofer Degdeg, do you want to unmute yourself? Okay, I can ask. Hi, Nelao. What are the types of sulfide minerals associated with fresh ore graphite? Copper sulfides, lead zinc sulfides, or molybdenum sulfides? Sorry.
Okay. Come again.
For weather ores, what are the associated oxide minerals, if any?
Okay. So for the fresh ore, the associated sulfide minerals, we have pyrite, we have chalcopyrite, we have pyrrhotite. Those are all mostly copper ion, and then we have sphalerite, which is now a zinc sulfide. We also have molybdenite, but trying to distinguish between molybdenite and graphite in this, it's quite difficult because they almost have the similar features. And now when it comes to the weathered ore, we have the jarosite, which is more dominating in the within the weathered ore, because the jarosite actually resulted, or it was a product of a weathering of the sulfide minerals. That's why on the weathered ore, which is from the surface up to the depth of from 12 to 20 there, you will not find sulfide minerals, but just jarosite. So that is weathering has taken place.
Okay, thank you. And there are any possibility of gold in both weather or fresh ore zones?
Come again? The possibility of what?
Gold.
Gold.
Yeah.
Let me say all the the results that the geochemical results, or even the study that I didn't find any traces of gold.
Okay, thank you very much.
Yeah.
We have another question from Evgen Kozlov. Do you want to unmute yourself? Okay, I can ask. Good day. Have you tried Raman thermometry to estimate the crystallization temperature of graphite? This is a popular user-friendly method.
Come again, you said the what? The thermometry?
Raman.
Oh, no, oh, that one. No, during this research, I didn't use it, although I considered using it. Yeah, but maybe in the future, I'll try to use it. Because actually it's like when it comes now to graphite, they are moving into using the Raman than the calcite, graphite isotope fractionation that I used.
Yeah, okay. So we have a question, another one from the YouTube. Give me 1 second. Okay. Does the biogenic source of the graphite suggest that hydrocarbon migrated into the host formation, or that it was in depositional?
No, I think it was in depositional, because this deposit has quite numerous quartz vein that are cross-cutting or within the quartzite, but you will not find graphite within this quartz vein. So I would rather say, or within just the fractures, you not find any like fluid deposited graphites. So I would rather say it's depositional, the carbonaceous materials were deposited there and then they went through metamorphism instead of them graphite being deposited from carbon rich fluids.
Okay, thank you, Nelao. I have one last question. I don't know if I missed it during your presentation, but you mentioned this direct proportion with the higher graphite content and the metamorphic rate. But there are any relation, any host rock is, I can say, better to have higher graphite contents?
Come again, you mean, you say the relationship between what?
You mentioned that there is a direct proportion of higher graphite and higher metamorphic rate. Am I right?
Oh, okay, I get you. You mean the other figure? Can I quickly just go back to that figure?
Yeah.
Are you talking about this one?
Yeah.
Oh yeah, no, this one is actually I calculated the degree of graphitization or the crystallinity.
Okay.
Which tells when metamorphism increases, the crystallinity of or the way the carbon materials or the graphite is ordered, it's also increasing. Okay. So you can see from this diagram that it's proportional or direct proportion, because you can see that when the degree of graphitization is increasing, the temperature is also increasing, which means metamorphism is also increasing.
Okay, and this is better for exploration, right?
Yeah, which means if you have a graphite deposit with such a figure, it means that the graphite is matured. It's of high crystallinity. It's matured for use in the industry, rather than when you have these points scattered or and not connecting in one point. I mean, like in one line.
Okay, thank you very much. Sorry, but it's a topic that I don't know a lot, so it's really nice. Thank you.
It's okay.
And I think we are done with the questions, Tom.
I got one quick one, and then yeah, we should stop. Just following on from that, Nelao. What really struck me was the big range in temperatures that you calculate from 400 to 700 degrees, and I'm just wondering what was the spatial scale that those variations were happening over. Were they right next to each other, or could those be regional metamorphic gradients, or must there be contact metamorphic gradients or retrogression?
You mean like from the samples that I calculated?
Yeah. So what I'm wondering is why you have this 400 degree values and the 700 degree values. Are they?
Oh yeah.
Yeah.
That is something I really maybe let me not give you an answer which is not making sense. Just like Kathryn said, I think these are the temperatures that you are talking about, where they just like what Kathryn said, that I think it would be good to look into contact metamorphism rather than just a regional metamorphism, because then you will be able to get more temperature which are meaningful. And also the other question that was asked from I think you were talking about this one, that was asked from YouTube, whether I have used the Raman thermometry. I think if I use that one, will give me much more appropriate or reasonable temperature than these two methods.
Yeah, I think potentially applying that Raman thermometry to mapping, looking at the spatial distribution of those peak temperatures could resolve that contact versus regional metamorphism question.
Regional metamorphism, yes.
Could I just say, I think you've probably got a lot of uncertainty in here. So you'll have localized intrusions, you'll have fluid flow along fractures, you'll have uncertainty just on the measurements, and these are, I guess, estimates rather than true measurements, aren't they, really? Because of the way they're calculated, there'll be quite significant uncertainties on them. So I suspect that all of that means that you're looking more at a range than sort of really specific temperatures, but I think Tom's right. It would be really interesting to see if you can see any spatial pattern in those.
Yeah, that would be good.
Can I ask one more quick question, please, Tom?
Yeah, last one.
Are there other deposits, other similar graphite deposits in similar kind of sedimentary units of the Damara origin?
We have some. We have the Black Range 72. It's they are schist and nice. So I haven't really looked into that one, you know. Yeah, but I think that one is also not far from the Okanjande graphite deposit because it's also within the Damara belt itself. Apart now from the vein type, which is far down south, hundreds of kilometers, which is hosted by granites of the Namaqua land.
Yeah. Okay, yeah. So this one is quite special, though.
Yeah.
It's interesting because Namibia is full. The Damara origin in general is full of quite special mineral deposits of all kinds. Yeah. Thank you very much, Nelao. That's all from me.
Okay, thank you. Thank you too.
Okay then. Anything more, Filipa?
No, I think it's all. Yeah. So
great. Yeah, I had the overwhelming sense that there's a lot of interesting work to be done on this graphite. I don't know if anyone in the chat. I think some grant reviewers would probably agree, potentially. So if anyone's thinking about writing a project, then I guess Nelao would be a fantastic PhD student to do it.
Oh yeah, actually, yeah, there's quite some work to be done on this deposit. There are so many things to consider, you know, even just the geochemistry itself, the geochronology, even now to focus on the temperature and the ore body itself. Why it's like complicated, because there are some certain faults, you know, that transcend over the ore body. So those are all the things that you know, research can be done on. So there is quite some work that needs to be done on this deposit.
Great.
So that it can be understood, yeah, better.
And your email is right down there. So
yeah, for questions, any questions, comments, suggestions, you know, that there is my email. Yeah, you can contact me.
Okay, I think we'll end it there then. Thank you very much, everyone, for coming. Thank you, Michael, Nelao, and especially Kathryn for your great questions and discussions.
Thank you
very much.
Thank you, everyone. And thank you guys for organizing. Fantastic as always.
No worries. Okay, I'll end the meeting. All right, have a good day.